So a few weeks ago, I saw my name listed on the agenda for this, and
To your great surprise.
Yes, you did.
I was delighted to do it, but I have to offer a few caveats to this also, which is I've been involved in the development of the aerosol models at NCAR now for the last 7 or 8 years, but I'm not involved in the I'm watching over the next one, but I'm not one of the principal players on the next generation aerosol model. So I'll tell you a little bit about what's going on there, and because I'm a little bit distanced from it, I haven't been keeping up on the literature as well as I ought to have been. So this was a good opportunity for me to review that as well. And then the last thing to say is, although I've participated on IPCC a couple of times in the past, this is the first time when I haven't been either a reviewer or a contributing author or something. So I'm not sure of what's in. I'm not sure of what's in the fourth assessment for the aerosols. I've been making educated guesses, and I don't know. Did anybody read the chapters that were directly relevant to aerosol and kind of have things memorized? Good. Guy can straighten me out here then if I go wrong. So I'm going to try and identify what I think are going on with current aerosol formulations, and then tell you what I think is going to come on board for the next assessment. And one of the points that I'll make a few times is that most of the viable parameterizations that I think are going to go into the fifth assessment already exist in experimental configurations, and it's mostly a matter of putting them together and then adding little bits together from a variety of places and making sure that their things still work well, understanding their interactions, and then it's going to be a pretty costly affair to do this. So we have to find the horsepower to run the kind of model that I'll talk to you about today. And then, of course, just the aerosols themselves aren't enough, that they interact with so many other pieces of the AOGCMS, as we're calling them here, that I'll mention a few things about what other processes within those models might require attention. And then discuss very briefly some of the interactions with the other components, the non-atmosphere ocean components. Thanks. So I just put this one up here to remind those of you who haven't thought about how aerosols are interacting, how things work. They basically are, they interact with every component of the climate system as far as I can tell, and via one means or another, either through modulating radiation in the atmosphere through clouds, through affecting what gets, acting as a transport mechanism for moving things between oceans and atmosphere or and land, for example, and also affecting surface fluxes of radiation and also various nutrients. Also, this little bulleted item or item called oxidation really represents all of the photochemistry that's going on in the atmosphere, and I'll talk a little bit about it, and it'll obviously connect up with things that Guy will talk about in the next presentation. Thanks. So there's a lot to talk about in this. I'm going to move pretty fast, but I thought I would at least remind you of the ways in which people have been focusing on aerosols in Earth system models in the third assessment, for example, in particular. And that, primarily they've been thinking about them in terms of climate forcing and characterizing them in terms of the direct, indirect, and semi-direct effects. And of course, I could spend an hour talking about any one of those, or probably about any one of the bulleted items, sub-items among those three, but I'm going to try and talk a little bit about all of them. And I really will just touch upon a few items within each of them. I'm going to focus on some of the uncertainties in the direct effect, primarily with respect to carbonaceous aerosols, and the potential for underestimating the role for secondary organic aerosols, and the fact that those aerosols, which are a very large fraction of the aerosols in the natural world and the Anthropocene, are sometimes assumed to be what are called organic aerosols and primarily scattering aerosols, but in fact are not necessarily so. And then I want to remind you of the fact that the interactions between the various aerosols can modulate the radiative and radiative properties of the aerosols themselves and their hygroscopicity. And those are some of the places where there are a lot of uncertainties in how, in the properties of aerosols with respect to the direct effect. The indirect effect, where aerosols are acting as a cloud condensation nuclei and essentially modulating the effect of clouds, both their optical properties and their properties with respect to the hydrologic cycle, have been recognized as potentially being a very important effect. And in the third assessment, their amplitude was a complete unknown, and their uncertainty was a complete unknown, in essence, where it was postulated that it could be as large as completely balancing the greenhouse gas forcing, but could also be zero. I don't know what's going to be said in the fourth assessment about that.
A lot of discussion to find out if it's poorly known or very poorly known.
But a number is given.
There is a number. Is there an uncertainty also produced?
Yeah, but it's -1, I believe, -1.2.
Okay.
Plus or minus like 180.
Okay. So, you know, the way it's been posed in the past is as changes to to the aerosols will change the number of cloud condensation nuclei available, which will in turn change cloud drop number, and thus influence cloud brightness and lifetime. And one thing to just remind you all of is that the focus to date, and I think the focus still today, is mostly on liquid clouds and their roles in stratiform, stratus and stratocumuli clouds, and there's been much less attention paid to strongly convective clouds. Although that's an area where there's a lot of interest and excitement, I don't see a path forward on that personally, so I'm not going to spend a lot of time talking about it in the context of this presentation. And then I'll also mention that the aerosol-ice interactions are as yet poorly characterized, and their role with mixed phase clouds are also poorly understood. And Ulrike Lohmann and her colleagues are the ones that I know who have spent most time looking at these problems, and maybe the rest of you can contribute on it, but I'm not going to say much about it for the rest of the talk. Lastly, there's what's called the semi-direct effect, and this is where the aerosols influence some other properties of the atmosphere, and those in turn have a further effect. And the first ones were documented by Ackerman in 2000, and Andy Ackerman in this case, where he identified the potential for aerosols sitting above boundary layers to affect the buoyancy profile and thus affect how clouds form and what the radiative properties would be of the aerosol cloud combination. And then he also documented the potential sensitivity of clouds to what I call relative humidity effects. That is, what goes on with clouds and aerosols will differ depending upon whether these aerosols and clouds are sitting below very dry layers or moisture layers. Something that's just come along relatively recently, and we're documented in a couple of papers by Graham Feingold and his collaborators, Xu and Jiang, were the effects of microphysics on shallow trade Q and stratocumulus. And what he was able to show is that in spite of the fact that the sort of well-known Toomey and Albrecht effects are solid with respect to their microphysics, there is more going on than just those two effects. And the interactions of the aerosols and clouds with respect to dynamics leads to some unexpected results. And in fact, what he was able to show in these studies was that injecting more aerosol into the clouds, which would, in the traditional interpretation, lead to longer cloud lifetimes and less precipitation, in fact, and potentially more clouds with higher cloud fractions. In this case, led to lower cloud fractions, thinner clouds. And this was essentially due to the interaction of the dynamics with the microphysics, and that the small drops evaporate more readily. And it's kind of interesting to point out also that the effects which are documented in this series of papers are somewhat inconsistent with the recent paper by Joram Kaufmann, who was able to document increases in liquid water path and cloud fraction associated with the presence of aerosols, but those actually occurred for larger clouds. And so the speculation is that, in fact, the effects can go either way depending upon the particular dynamical circumstances. Next, please. So now I'm going to jump back to what are were present in most, I think, of the third assessment and fourth assessment models that treated aerosols. They're usually identified as what are called a bulk formulation. And that's a formulation in which one predicts the time evolution of aerosol mass mixing ratios only. Frequently, the aerosols are treated as external mixtures. That is, although they can exist in clumps, each of the clumps is a discrete entity and a discrete type of aerosol, and their radiative properties are distinct from those kind of aerosols where you might have one substance encasing or enclosing another. In the model that we use, and I think many other modeling groups around the world, we've typically been willing to represent sulfate aerosols, organic carbon, what we call the sulfate aerosols are assumed to reside in a fine mode, submicron mode, and they require a little bit of photochemistry. The source precursors and some oxidants. Hydrogen peroxide I should have named off ozone and OH as well. Organic carbon, which is also assumed to reside in a fine mode, and we typically assume resides in both, exists in a hydrophobic and a hydrophilic mode. That this is assumed to be a scattering aerosol. Black carbon, which is a strongly absorbing aerosol that also sits in a hydrophilic and hydrophobic mode. Dust, which resides in a range of sizes and frequently is divided up into a number of bins, 2, 3, or 4. And sea salt. If you add all of these together, you get about 15 species which are required to predict this slew of aerosols, over and above the 7 that kind of form the basic model variables for an atmospheric GCM of temperature, winds, mass, and then water, vapor, liquid, and ice. And a typical kind of cost for a model like this is somewhere between 20 and about a factor of 2 overhead compared to a simple model in which we prescribe the aerosol distributions and don't do any photochemistry. So the first...
20 to 200 is probably right. It's got to be 120 to 200.
Well, 20% overhead to a 200% overhead. So
up to a factor of 3.
yeah. Now, the initial aerosol studies that were done were primarily focusing on the direct effect, and the first attempts to study the indirect effect did some very simple things, and one of the earliest studies was the stuff that Olivier Boucher, who's here, and Ulrika Lohmann did, in which they attempted to map sulfate aerosol mass to a cloud drop number, and then allow this to affect the cloud brightness, for example. And one way of characterizing these ways of producing estimates of indirect effect, in this case the Albrecht effect, is an empirical representation, but there's also representations which attempt to map from a particular aerosol size distribution to a cloud drop number. And this kind of a formulation, or from an aerosol size distribution to a CCN distribution. And from the CCN distribution, you can determine, given a number of other meteorological parameters, how many of those potential CCN actually activate and form a cloud drop number. Kathy, do you want to hit it, or shall I? There were problems noted early on with the empirical approach, and these relationships which are the relationships which were derived have been shown to be kind of region and regime dependent, and there are a bunch of I'm showing you a bunch of different relationships that were derived for this for different field experiments and different studies. And depending on which ones were used, you can derive different indirect effects, ranging from a low of about 0.4 to a high of 1.8 for the indirect effects. And so because of these kind of uncertainties, it was, most groups have tried to move from this empirical technique to more physically based approaches. And so I was telling somebody earlier on about a talk I gave in India once in which the power failed in the middle of the presentation, and so I just went up to the window and held the transparencies up and said, if you could see this transparency, I would be telling you this. Guy, can you back up one and just make sure that we're on the right one? I can't. Yeah, okay. So maybe these are a little bit out of order. Let's go forward again.
Forward?
Yeah, okay. So I guess I'm going to jump now to a description of sort of a summary of where I think we were for the fourth assessment, and then maybe where we're going as well. My impressions from knowing about the various models which are out there and having read many of the papers I think that are entering into the next or this assessment was that about half of the models were using a bulk formulation that didn't predict aerosol number or have any means of predicting the evolution of size distributions. And they left out a lot of processes that we know to be important in understanding aerosol formation and their role as cloud condensation nuclei, for example. I think most of the models focused primarily on direct forcing. Most of the models explored changes only to sulfate and black carbon. If they did treat the other aerosol species which I've mentioned, my guess is that they fixed them. They assumed there were no changes in dust, no changes due to natural fires to sea salt, for example. Most models will have completely ignored nitrate aerosols and treated secondary organic aerosols, those which convert or which are produced in situ rather than being emitted at the surface extremely crudely. And my speculation is that all of these items are going to change very substantially in the next generation models.
Say half of the model have a good formulation. The other half doesn't have anything at all. Or they have something better.
They had something better, I think. You don't think so? Was I giving them more credit? Okay, that's fine. So, I know there's a few models in which they did better than just a bulk formulation.
One
David.
thing to recognize is that a lot of the AR4 runs, because of the time delay necessary, were made with versions of the model that didn't necessarily include all the sophistications that had been developed during time.
Yeah.
So
Certainly that was the case for us. David.
And so what you say that the AR4 models actually did in terms of crudeness is not necessarily representative of what the state of the models is during the AR4 period.
Yeah. Steve, you had a comment.
Is it very common for, you mentioned black carbon, do pretty much, if they do black carbon, do they do organic carbon as well?
They do. And usually they make an assumption about the sort of yields of secondary organic aerosol that are associated with the emissions, either natural or anthropogenic emissions from the various sources. So they produce a secondary organic aerosol, but it's very crude. That's right. So there are a bunch of other options other than the bulk framework that I talked about, and these are named here. You could argue that this bulk formulation falls into the category of a sectional model, in which each of these, this is supposed to represent aerosol size along the abscissa and mass, let's say, along the ordinate and or number, and the different colors, different aerosol types. And so this might be considered to be the kind of a model that that many of the modeling groups were currently using, but there is a move afoot to move to these other formulations for representing aerosols. And all the formulations provide some mechanism for identifying a varying size distribution that predicts drop number as well as mass. And yeah. The treatment that we're moving towards for CAM4, I've identified here, is going to have about 7 different categories. And within each category, we monitor a number and then the mass of certain components. So the Aitken mode is sort of the ultrafine mode, which through coagulation and accumulation processes changes to larger modes. And then there are a few bins with very large modes. And in each of them, we carry a number and then can carry different components which are represented according to certain mixing rules within each of the categories. And if you were to add all of these things up, you'd come up with a total number of tracers ranging from between about 25 and 33. This is over and above the first generation model that I was identifying as having maybe 10 to 15 tracers. And then you have to probably add another 5 to 10 precursors and oxidants to the list of variables which would need to be solved for in the atmospheric general circulation in the context of this framework.
Does this include internal mixing?
Yes, it does. And then I'm at the far end of the spectrum of complexity that people are considering are the kind of models which were developed by John Seinfeld and his students and postdocs. I'm showing you here a set of, a framework that was developed by Peter Adams. It's called a two-moment sectional algorithm, where you essentially divide the spectrum up again into a number of categories and then represent a couple of pieces of information within each category. And Peter's claim is that in order to do this problem right, you need about 30 sections ranging over these sizes. And then within each bin, you would carry a number and, again, carry the amount of mass that's mass of each of the aerosol species or aerosol components within those sections. And the formula that you would get for calculating the number of advected species here is 30 bins times the number of species plus the number of particles within each of the bins. If you do the math for these species, you get about 180. So this is the number, the high end of the number that one might consider.
It doesn't give you any information on internal mixture.
That's right. Again, you have to make assumptions about what the internal mixture is.
So you actually would want to have maybe some internally mixed, externally mixed.
Yeah.
So you
So
may have
again,
to add to that. And you're still not at the range of new particle formation either.
Now, yeah, so JF, Jean-François, is also putting together one of these very elaborate formulations, so he can probably answer questions better than I can on it. But Peter has also pointed out that these models which make an assumption about the shape of the size distribution have some problems, and that if you were to measure size distribution and then attempt to fit it with one of these prescribed distributions, you're going to make mistakes. And these small differences can have important consequences in the formulation of the aerosols. So he chose a particular example, which I've borrowed from him unabashedly, and what he's done is to show what the consequence is of looking at the evolution of the size distribution of a simplified scenario that involves only the emission of SO2 and its subsequent oxidation to sulfate. And essentially what he's done is to make the assumption that either all of the emissions go in as SO2 or that some of the emissions go in as particulate sulfate. And the reason that this is important is because if there is no existing particulate sulfate, then all of the emissions act to initially produce a lot of ultrafine particles, which will undergo a different destiny, if you will, than if there is a set of particles already existing in the air parcels which the gases can condense on. So this 5% of the anthropogenic emissions which are injected as sulfate really make a very small contribution to the sulfate mass, but have a big change in the evolution of the species. And what Peter is showing here is the vertical profile of the resulting sulfate aerosols. The green line is sort of the background sulfate aerosol distribution. The black line is the profile that one would get if you inject all of the SO2 or the sulfur as a gas. And the blue line here is the vertical distribution if you inject some of it as particulate matter. So you can see there's about a factor of 2 difference in the vertical distributions there, and a very different distribution of the or size distribution itself near the surface, with a much larger mode for one of the emission scenarios. Guy? So another thing that has been ignored up to now in formulations in global models is the role of various other atmospheric constituents on influencing aerosol's destiny. And in particular, surfactants and organic films can affect cloud drop activation and their subsequent scavenging. There is some work being done by Thanos Nenes and his colleagues very recently in trying to acknowledge these things. Lastly, another treatment that's been ignored up to now, or phenomena that's been ignored, is the role of carbonaceous or absorbing aerosols sitting inside a cloud drop, which can heat and thus affect the subsequent growth of the cloud drops and their activation. Another process which has been ignored, and now we're moving from the formulations of the microphysics themselves to the peripheral, what I'm identifying as peripheral physics, is the need for understanding the subgrid scale variability of the state variables of the model on the evolution of the aerosols themselves. In particular, one of the things which we believe important is to represent the subgrid scale variability of water vapor, of precipitation, of radiative, and the clouds themselves in terms of their effect on the radiation, photolysis, and indeed on drop activation. And there are a number of groups around the world who have begun to try to represent this subgrid scale variability. Many of them are working in the context of what are called probability distribution function approaches. The first ones were by Adrian Tompkins, and there have also, who did it for, I think, for water vapor only. Steve Klein and Christian Jakob then examined the influence of this on cloud microphysics, and Robert Pincus on radiative transfer. The subgrid scale variability issues have an effect on both the microphysical side and also on the direct effect, and there was an early study by Jim Haywood in which he was able to show that if one calculates the direct forcing with or without this subgrid scale variability, it actually makes quite a difference in the picture that you get of radiative forcing. If you do it if you composite the information about subgrid scale variability and do it on a GCM length scale, you'll get one particular forcing, whereas if you acknowledge the subgrid scale variability and the hygroscopic growth that's associated with it, you get a different picture of the radiative forcing. So I mentioned at the start of this talk that we tend to almost all of the models that I'm aware of today have tended to categorize carbonaceous aerosols into one of 2 different categories. Either a scattering aerosol, which we typically call organic carbon, that has a lot of hydrogen and oxygen tied up on it, and black carbon, or an absorbing aerosol, which we tend to think of as being elemental carbon. But there's become a recognition very recently that, in fact, there are a lot of organic carbons out there that are strongly absorbing, and they have to be treated differently from the way we have historically been treating them. I'm showing you here a couple of petri dishes containing, or air filters actually, I think, containing different aerosol masses, or aerosols that appeared in a paper by Andy Andre, and I don't know how you say his last name. Maybe somebody here can offer it up. But what they've done is to point out that this is an uncertainty which ought to be considered in characterizing aerosols in the atmosphere and what their impacts are on climate models. They discuss this typical characterization, and then point out that many of the aerosols are strongly light absorbing and appear black in the visible, as I showed in that previous slide, but they're not elemental by any means. And they're indicating that, or they've pointed out that part of that the result of this simple interpretation leads to a miscategorization of the aerosols, both in terms of their optical properties and the consequences for the way they work in the atmosphere. These carbonaceous aerosols are weakly absorbing at the wavelengths that are typically used to sense aerosols both remotely from space and also in situ measurements. But because there is so much of these aerosols, if you even make a small, there are maybe 10 to 100 times more organic, more carbonaceous aerosols that are tied up in the organic state than there are black carbon aerosols. So if you even make a few percent error in your characterization of what you're calling carbonaceous aerosols, then you're miscategorizing a fraction of the aerosols which can be as important as the black carbon, the elemental carbon that towards absorbing in the atmosphere. They're also pointing out that there are strong absorption features in the ultraviolet from these brown aerosols, and that'll have an effect on photolysis, for example, for ozone and tropospheric photochemistry, and that a significant fraction of the mass in these absorbing aerosols is soluble in water, and whatever dissolves in cloud drops can also contribute strongly to changing the absorption of the clouds themselves. And for particular mixing ratios, which I'm not going to get into, they've shown that you can change the absorption characteristics of the clouds by as large as a factor of 6.
Can you observe these by satellite, the carbon aerosols?
Yeah, but you won't. You can tell there's aerosols there, but whether the characterization of, yeah, you can tell the aerosol is there easily, but identifying what kind of aerosol it is another matter. For any of the aerosol types, really.
For an alpha.
Yeah. David.
And actually it's been pointed out by people like Pierre Biscay that even when you have an aerosol and you look at it under a microscope, it's not so easy to figure out what that aerosol is.
Yeah. So then I'm going to jump. How much time have I got now? Oh, good. I'm doing great. Then, well, pretty great. Yeah, including questions. Okay. So I'm going to spend a little bit of time showing about how these aerosols might interact with other components of the climate system. As I mentioned earlier on, these secondary organic aerosols are a potential problem. They're treated very crudely. We know that they are an important component of the aerosol mass in the atmosphere. The assumptions for the models which were coming from up through the third assessment were that 90% of these aerosols were from biogenic emissions, and I'm going to show you a bit of evidence that that's not necessarily true as well. And then I'll show you one example of dust. So this work is following on the work of Colette Heald, who's sort of identifying to you the sort of classic picture of how secondary organic aerosols might form in the atmosphere. A typical thought was through production from biogenic sources, through monoterpenes, and then aromatics coming off of petroleum products. And then as well as direct emissions through fossil fuels and biomass burning. And the organic aerosols, which are primary organic aerosols, are thought to be between 10 and 30 teragrams of carbon per year through the biomass burning sources and 45 to 80 through fossil fuels. The guesses that people have made in the past for secondary organic aerosols is that there were between 8 and 40 teragrams of carbon being emitted. Now, there were a recent series of studies that took place from Asia, which were really the first set of measurements that attempted to look at what organic carbon looked like at altitude in the free troposphere, and they measured as high as 6 kilometers. And I show you here a set of 3 profiles. And the black line here is showing you the profile, the mixing ratio of organic carbon as measured by a number of instruments. There was an enormous effort to get to try and assess and characterize the aerosols from more than one instrument pack for this field program, and these numbers are believed to be really quite solid. The red lines here are our attempts, or a modeling group attempt. In this case, it's the Harvard GeoChem model, to represent to capture these profiles through a model simulation. And what you can see is that in each of the 3 studies that I cite here, that there are underestimates between a factor of 10 and 100 in the free tropospheric organic carbon aerosols. So that begs the question, what is it that is responsible for this? And the first thing that I want to point out is that it is not the case for many other aerosols that we can't quantify or simulate in a reasonable fashion what goes on in the atmosphere in these particular model areas. And so I show you here the profiles for sulfate and elemental carbon, or black carbon, and you can see that the model and observations are reasonably close to each other. So the thought is that many of the transport and scavenging processes have to be done, as well as emission inventories have to be reasonable for some of the other species. And we can go on here, Guy. Now, there are a variety of other studies which have also suggested that there's an underestimate of secondary organic aerosols. In this paper by Volkamer et al., they've attempted to sort of characterize it in terms of a photochemical age. And what they've done is to show the red line here being the line in which the secondary organic aerosol measured corresponds to that predicted by a model. This is for a Mexico City study, a US coastal outflow study, and then ACE Asia, which I've already pointed out to you. And you can characterize it in terms of a photochemical lifetime. And what you see is that the longer the photochemical lifetime, the higher this discrepancy is in the emissions, indicating that it's probably something going on in the free troposphere itself, and that's arising in situ. So Colette has come up with a variety of other explanations for this, and Guy, I think if you hit that it's possible that isoprene is also contributing to the production of these reactive organic gases, and then they subsequently form organic carbon, as well as, and hit it again, that there may be other photochemical pathways which will result in more rapid production and oxidation of the organics. And then lastly, that it might occur through cloud processing. So at this point in the game, rather than the 40 to 80 teragrams that we had before, the speculation is in fact that there might be much higher emissions of the precursors to the organic carbon aerosols. And I'm I'm just outlining to you here some of the ways in which this secondary organic aerosol formation might be driven by climate change as well as influence climate change. And I'm going to lastly jump to showing you one result from a study by Natalie Mahowald in 2003, in which what she did was to, rather than to look at some of the more traditional for the aerosol climate science community set of aerosols like carbonaceous or sulfate aerosols, but looked at what could be happening in a changing world to atmospheric dust. Natalie's assessment through a set of experiments, which I'll tell you a little bit about here, is that the current anthropogenic contribution to aerosols or to atmospheric dust could range from 24% of the current, well, let's say, removing the anthropogenic component of the dust sources could result in a reduction of as much as 24% in the global burden of dust, or an increase as high as 60%, depending upon the particular scenarios that you put together. And what Natalie has done is to make a series of runs in which she has looked at changes in soil dust due only to changes in moisture availability and surface winds between past, present, and future climates. And that's indicated by the white line that you see here. And what you see is that as we move to a higher set of greenhouse gases or anthropogenic forcing, the global burdens of dust aerosols go down to one in which she's inserted a dynamic vegetation model, biome 3, which is capable of responding to changes in temperature, precip, and cloudiness, and to allow the vegetation itself to evolve. And what you see there is that using those scenarios, which are indicated by the blue line here, that the burdens are a maximum in present day and were actually lower in pre-industrial and will be lower in the future, to a result in which she also allows CO2 fertilization to occur in biome 3, and then a set of results in which she begins to try to account for cultivation as well. And I don't have time to go through all of the scenarios. But the point is that they're all over the map, but they depend strongly on considerations which haven't typically entered into our previous exploration of climate change and aerosols. And I think, okay, I'll go through this very rapidly. There are a set of stations, about 180 stations over the globe, which are attempting to characterize aerosols. They're known as the AeroNet sites and documented in a paper here. And what these panels show are time series for two model configurations and comparing the results of a set of model runs, and the different kinds of aerosols are indicated here in colors, to a set of measurements from these three different entirely independent measurement programs. AeroNet, which is a surface-based site, and two products that come from the satellite community, MODIS and MISER. And it's quite hard to see, but the black dots that you see here are the surface-based estimates of aerosol optical depth. The gold dots are MISER and the green dots are MODIS. And the point that I want to make is that the observations for these sites vary dramatically, easily by a factor of 2. These are the best products that we have today for characterizing aerosols from space and from the surface, I think. And also that some of the retrieval techniques are not as good over land as ocean, but we believe most of the attention has been focused particularly on the satellite products and attempting to produce retrievals which are good over the ocean. And They differ just as strongly over the ocean as they do over land. And so I guess, yeah, I'm going to move to the summary and conclusions here. The next generation models will be comprised of formulations that probably already exist. There are a whole lot of different things that we're working on to improve those, the frameworks that we used for the previous assessment efforts. We're attempting to calibrate these models through a variety of different observations, but there are still a lot of inconsistencies in the observations. We also, because there aren't enough observations, we're attempting to use higher models, either large eddy simulation models or LES models, as well as parcel frameworks to calibrate the parameterizations which are used in the global context. There are every day people come up with a new mechanism for the potential importance of aerosols to climate change problems, the challenges in trying to quantify their role, and to calibrate these mechanisms, most of which I believe really exist in global models. And it's very easy to envision the cost of the next generation atmospheric models going up by factors of 5 to 20 over the models that were used, what I'm terming moderately costly models of the fourth assessment. And who knows how expensive it'll get if we include a really our best shot at reactive photochemistry. We can hear about that from Guy, and that's the end. We don't need that one. So I'll close. David, yeah.
Can I make a few comments about one component you didn't discuss?
Sure.
IPCC broke up the indirect effect, as had been done by others, into two components. One, the cloud brightness aspect, which they called the radiative forcing, and that was the minus 1.2 watts per meter squared. And the cloud lifetime effect, which they said, oh, that's a hydrologic thing, and we're not discussing that. So it wasn't really in Chapter 2, which is the radiative forcing. Well, it's discussed in Chapter 2, to some extent. So the next in order to do that second part, the cloud lifetime, what really has to be done is the counterpart to this aerosol component in which you have a size distribution of aerosols. You need a size distribution of water droplets for the clouds. So then you could look at cloud condensation nuclei and how it varies the change in cloud droplet size and how it impacts precipitation efficiency, which is sort of a big deal in terms of what the cloud feedback is actually going to be for both for convective clouds as well as stratiform clouds. So a major question, and we at GISS are sort of involved in wondering about this, is can you really do a cloud water droplet distribution without getting into the realm of science fiction to the nth degree, basically? How do you do this? Is it possible to do it? Should you waste your time and energy in doing it?
Yeah.
And but the second aerosol indirect effect is directly associated with that component. I have no idea what's going to happen. I'm pretty sure that by the time of AR5, there won't be anything done definitively. But I don't know what modeling groups are going to do in terms of how much energy they're going to be using on trying to get cloud droplet distributions as part of their standard cloud model.
I know that there are models, and they've been in existence for 10 years, that include size-resolved aerosols, size-resolved ice particles, size-resolved liquid particles, and maybe even can distinguish the different contributions to the aerosols themselves, in particular the work by Lamb and Chen, for example. But those are parcel calculations, and they're enormously expensive just to do the calculation for one box of a few meters on a side, much less to try and do that kind of thing in the context of a global model.
I think David is absolutely right. The complexity of aerosol scheme in GCN has increased much faster than the complexity of the cloud scheme. There is now a bit of a mismatch between the two. We cannot connect them very well, as well as we should. It's interesting to see that different groups are taking very similar directions for modeling the aerosol in GCMs. And starting with M7 the German M7, we have these 7 modes of aerosols where you predict number and mass for each mode, and then UKCA in the UK, which has a very similar approach as M7, and then Steve's GAN.
Yeah.
So probably the original idea was good.
So, if, say you were able to magically turn on all these aerosols, and it costs 20 times more, whatever it costs, and run it, and one of the things that we always have to do is try to get zero net energy balance at the top of the atmosphere in the coupled model. If you had all those things in there, would you still be able to do some tuning with it, or would the tuning problem just become so...
Yeah, there's still lots of things to tune.
Clouds.
Yeah.
Yeah, so you still have to do all of that. I guess you have knobs.
It has to
Every
do
one of
with,
these has
that's right, it
knob.
would have to do with characterizing the subgrid scale variability of the convection, or of water vapor, or of the vertical velocities associated with convection, or something. But yeah, or the scavenging parameterizations, which, well, maybe the scavenging parameter overlap, let's say overlap, rather than scavenging itself, would easily have a very strong effect on the radiative balance. So yes, there would be ways to tune it.
If you could turn on everything Jerry talked about, is your hunch that the net would be greater or less than minus 1?
I have no hunch. I mean, I think it could go either way very, very easily. My feeling about, I mean, are you asking about the total aerosol effect or the indirect effect? My feeling is that if if aerosols had as big a role to play in the climate system as some early model results suggested, like changing the model by 5 watts per meter squared at the surface globally, we would have seen it. And the fact that we can't point to it that easily means these effects are not that large. But other than that, I don't know which way they're going to go. Nor?
I mean, you've also raised the other point that to do all of this, you also need to rely on other parameterizations like vertical velocities in clouds, which may be highly uncertain as well. So I think maybe the fundamental question is, do we know the sign? And what do we have to do to get the sign resolved? And how important is it beyond that? Because I can't personally see, mind you, I'm getting out of the business, but I can't personally see spending a lot of computing resources to add another 300 species, so that you can answer a question that's not the fundamental question, maybe, or maybe not the most important question. So clearly somebody has to show us whether we really need to do this.
Yeah, I guess I think that the issue is, I mean, what are these models after all? But they're just a mechanism for doing a problem that's too hard to do in our heads, right? And to allow you to sort out what the contributing factors are towards the complex interactions that go on in the climate system. So you need, if we were to build this incredibly complex model, you need to be able to sort out what the uncertainties are and identify which ones of them are the most important as well. Right? Peter, yeah.
You've got quite a few global observations which suggest that the scientific go for the direct and the indirect.
I mean, is this value of minus 1.2 that's quoted the largest radiative process that most models don't presently have?
I don't know.
No, some models have an indirect effect in it.
Yes.
Yeah, but I'm saying several, including ours, doesn't. So is this the largest radiative signal that isn't in those?
You mentioned Peter Adams' work. One of the things he actually showed in using this more sort of complicated scheme was how the importance of nitrate aerosols goes up.
Yeah.
And so if you want a bottom line result, it is that maybe you're going to be underestimating certain types of aerosols if you don't use the more complicated size distribution.
But there are effects like this change in the absorption of clouds in the presence of these brown aerosols, which aren't even in the models at the moment. And there is still this, it's anomalous absorption that I don't think has ever been completely resolved for in the atmosphere, which might be explained by some of these things too. So there may be parts of the puzzle that we don't have a handle on yet also.
Yeah, Phil, I want to ask you about on the production of VOCs side. Is that, I'm just naive about these models, but is that coupled to the land surface
Yes.
parameterization? So, for example, evergreen trees do different things than grasslands.
Yeah. So the work that's going on at NCAR is being done by Alex Gunter and his group, and they are attempting to tie intimately the emission of these precursors to the organic, to the plant functional types that are embedded in the land model.
Right. So have there been studies that take the next step and look at changes to the emissions of VOCs due to changes in plant functional types?
Yeah.
What do they say? This problem's going to get worse or better?
I'll show you a little bit.
What's that?
I will show you a little bit of it.
Nice segue.
One question now. Can I just? Okay, on the global scale, you know, the aerosol effect, direct and indirect, is we don't know -1. What about on the regional effect? I mean, do you think that there could have been some perturbations that are large enough to be of great importance? And you know, we always talk about the average, but of course, Paul Crutzen will say the brown cloud is a study what.
If you look at,
so how do we have? What do we have to say about that?
well, I mean, I just think the amount of aerosols that reside over Southeast China must be extremely strong and must be having a demonstrable effect on a variety of things. Plant productivity, potentially, well, certainly health. I mean, and certainly the energy balance at the surface, I think.
Could it trigger effect and then through some teleconnection finally have some global impact that might not appear in the fossil? In other words, the effect of aerosol may be larger through some dynamical teleconnection than the average forcing. And when we talk in terms of average forcing.
Maybe. I don't know what the right answer to this
about this average forcing of what?
I agree.
Which masks a lot of probably other effects.
Do you have a comment?
For one thing, the regional effect, when we just thought it was sulfates, it was clearly cooling in the region. But now that it's sort of a mixture of these different aerosols and also a lot of pollution regions and a lot more tropospheric ozone, it's not clear what the forcing sign is always regionally. So when people first looked and said, oh, eastern US and Japan, they're cooler, I think it's more complicated now. I think we have a greater degree of sophistication about that. So who knows what the regional effect is.
Ready for me to come down?
Sure.
Sit
We can
down.
talk more about this later during our breakouts. So